Friends, welcome to the Brain-Machine Interface and the Neuromodulation Forum at the 2022 Beijing Brain-Machine Conference. I'm Li Luming from National Engineering Research Center of Neuromodulation, Tsinghua University. As we know, neurological and psychiatric disease are among the most prevalent threats for human health. Over the past decades, technologies in the field of brain-machine interface and neuromodulation shed light on the diagnosis and intervention of many brain disorders. This forum features a series of invited talks by leading experts on brain-machine interface and neuromodulation technologies for human. It will connect researchers from the different disciplines like medicine, neuroscience, neuroengineering, and artificial intelligence together to discuss current challenges, share ideas and expertise, and inspire promising future directions. I hope you enjoy the forum. Thank you very much.
Okay, so the next speaker is actually myself. Yeah, so I'll introduce me on behalf of Professor Luming Li, our original moderator. So our next speaker is Yanan Sui. Yanan is an associate professor at Tsinghua University working on machine learning, neuromodulation, and robotics. He got his bachelor degree from Tsinghua and PhD from Caltech. He also worked as a postdoc at Caltech and Stanford before joining Tsinghua. Yanan developed safe machine learning theory and methods for online reinforcement learning with unknown safety constraints and with implicit preference feedback. He also works on AI and advanced computing techniques for healthcare. He was listed as one of the MIT TR35 in China by MIT Tech Review with highlighted work on AI and neuroengineering. The machine learning methods he developed led to the eQuart 2020 Best Paper Award and were used in clinical treatment for neurological disorders. All right, so with this introduction, I'll start with my talk today. Let me start by sharing the slide. And now can you hear the full screen slide as I'm showing right now? Yeah, so if it works, I'll just move on. Okay, just tell me if the sound or the audio doesn't work, because there are no other moderators. Yeah. So the topic for today is learning and optimization for neuromodulation, restores motor function for complete paralysis. I'm Yanan Sui. I'm an associate professor at Tsinghua University at the National Engineering Research Center of Neuromodulation. So we start from the human nervous system. As we know, this is the Beijing Brain Conference. A lot of speakers are focusing on the brain, but our topic for this talk is more focused on spinal cord. Spinal cord is the shadowed area which bridges the brain and the peripheral nervous system. And spinal cord injury, as shown on the right, typically due to car accidents and other things, is like the red line. There is a virtual and physical cutoff, which of the spinal cord, which often causes disabilities in strength, sensation, and other functions below the site of the injury. Our goal for this work, and which I'm going to deliver in this talk, is how do we restore motor functions for complete paralysis? We want the paralyzed patient to be able to stand, to walk, to come back in more aspects in their everyday life. And I won't be able to cover all the aspects of this whole work. I'll mainly focusing on some computation and modeling parts. So first, let me have a brief introduction on spinal cord injury. I previously mentioned what is spinal cord injury, and the cause of spinal cord injury is actually mainly physical. The largest part is due to traffic accidents. We also have doing physical labors, falling from high places, doing sports, and the victim of violence, they are the major causes of spinal cord injury. So as we know, this injury is an injury for young adults. Many of the patients, they are young adults, and there are tens of millions of patients worldwide. In China only, we have more than 3.7 million patients domestically. And how do we treat spinal cord injury today? So the very standard training include physical training plus some chemical drugs. And these days, scientists are looking into more advanced methods like tissue engineering with stem cell therapy, hoping to have some neural regrowth on site on the injury site. The approach I'm going to introduce today is a quite different one comparing to the previous standard ones. We're using epidural electrical spinal stimulation for the treatment. So what is epidural electrical spinal stimulation? It's actually by implanting a stimulating array and a following stimulator into the spinal cord of the patient. So here in the middle, you see a CT scan with a spinal cord injured patient and the neural implant. So this implant will be controlled and with proper stimulation, the patient may be able to regain some motor functions. There are many, many questions surrounding this motor restoration thing. So first, what are we exactly stimulating? Are we stimulating the spinal cord, or we're just stimulating the dorsal root connecting to the spinal cord? This part we don't know. And what is the mapping between electrical stimulation and their motor functions? Are there spinal computations get involved? We think so, but we don't have a very clear understanding. Are there commands from the brain? Of course, because typically for every spinal cord injured patient, those accidents won't cut 100% of the downward neurons. But still, a lot of those patients, they are motor complete injury, but they still can send some command from the brain. How does those commands get involved with spinal computation together to achieve some possible motor control? This part we don't know at all. And most importantly, or most practically, how to achieve motor function restoration? Our answer to those questions are all unknown or not clear. We don't know exactly what happens in the injury and what happens in the following spinal cord neurostimulation. So how do we approach this question? We first do neuromusculoskeletal modeling for epidural spinal stimulation. We want to build computational models for us to better understand and to predict the neural behaviors. We then taking advantage of the models to optimize the design of electrode array, because the array I previously shown you in the slide was actually not designed for the treatment of spinal cord injury. It was designed for back pain. How do we design better electrodes for spinal cord injury? That is also a very interesting thing we want to look into. We also want to optimize activities of muscle, standing and walking behaviors with human in the loop. Here with human in the loop, we mean with both the clinicians and also with patients consideration into in this loop. So in general, what did we do? We do modeling of the whole system. We do the design of the hardwares and the softwares. We do the algorithmic optimization, and we do the real therapy applied to the patient. So let's start from the neuromusculoskeletal modeling part. And our goal is very simple. We want to match simulations with the physical experimental results. We first develop high-precision personalized spinal cord models based on magnetic resonance imaging result, which can tell us how does the spinal cord actually look like. We model nerve fibers in variable cross-sections of white matter and gray matter, and also with the neural roots. We do multi-diameter axon simulation with the help of the Neuron platform, which is a very popular neural computation platform. We also do the musculoskeletal simulation based on the OpenSim platform. We build a model with multiple major muscles that get involved with human standing, human walking, the major movements, and we're trying to simulate and let it move in the simulator. On the personalized spinal cord modeling part, we developed this high precision personalized spinal cord as we've seen on the left. So this is from the patient's MR imaging. We do this reconstruction, and also we do the electrical property reconstruction, and do embed axon models to calculate neuronal responses to stimulation. So here you see that after an electric shock from the outside, at some point there are neural responses, and at some other cases that the stimulation are not that effective, there are little or no responses, considering that the activation is not strong enough. So after personalized model, we also build average spinal cord model. So these average spinal cord model are based on anatomical atlas and statistical data. We use the average model of T12 to S2 areas of human spinal cord to represent our mostly interested stimulating sites. And the neuron pools of different muscles that are mapping from the spinal cord to the specific muscles were added to the spinal cord based on clinical experiences from the literature and from the experienced physicians. Okay, so with this personalized and also with the average model, what can we do? We can quantify the capability of stimulation. Can we do specific, precise stimulation for each individual muscle, or even for each individual neural bundle? We need to define selectivity index for muscle-specific stimulation, which means that we need to figure out some index or some metric to representing whether we are able to stimulate just one muscle without interfering any other muscle's activity or not. And with this new design metric, the selectivity index, we calculate and compare stimulation selectivity of different parameters. As I mentioned, that we have new designs for the electrode array, which I'll describe the details. We need to calculate how those stimulation actually perform. We need to use this metric. Okay, so how do we actually design and optimize the electrode array? We use the model of spinal cord together with the model of electrode array. So here on this figure, you show that this is actually the combination of a hybrid model of spinal cord and the model of spinal electrode array. The hybrid model of the spinal cord doesn't change, but the model of spinal cord electrode array is changing from for each loop. So here, the added model go through the simulation of spinal cord stimulation, and we use Bayesian optimization to do the updates and to provide new suggestions for a new model of spinal cord electrode array. Then we apply this new array to the model of spinal cord and do it again. So with the help of physical simulation plus Bayesian optimization, we're being able to calculate which spatial placement of those electrodes could provide us a better stimulating effect. This is our major parameters to optimize for electrode array. We optimize the length, we optimize width, we optimize density variations, and also the arrangement of contacts. We're looking into the number of electrode arrays with no more than 32 channels. So we focus on the electric field generated by the arrays, and we compare the new 32 contact array, which I mentioned that based on our current technology, we could support as many as 32 channels. And we compare that with all existing 32 and 16 channel arrays, and we also compare staggered arrangement and neatly arranged of contacts. So they are spatially with spatial different contexts. So the results is basically showing that our new electro design is achieving the best average selectivity index score. Okay, so with the new stimulating array, and with some we could implant it to the patients and start doing experiments to see how those electrodes, how those stimulating patterns actually perform. And this slide, we're starting to show that the results of stimulation and experiments. So these are 4 interesting patterns. There are also quite normal patterns we provide to the spinal cord stimulation system. So those are actually applied to the patients. And here are the questions. With the same stimulation amplitude, we tune the amplitude to be the same. Which pattern will induce stronger responses from the patients? And which would achieve better selectivity from left to right? And which muscles will actually be activated? Without doing the modeling, we actually cannot have much understanding from human experience, no matter that's very experienced physicians or any other one. But we can use model to do that. Let's start to see their actual stimulating performances. So here are those 4 bottom plots showing that x-axis 12 different muscles and y-axis different stimulating amplitudes. So basically, we can see that pattern 943 and pattern 998, they perform quite strongly, and which ones are more symmetric and which ones are not. Let's look into individual ones. So those are the experimental results, configuration and the real EMG signal collected from the patients. And on the right, we show the simulation results. Those are the calculated activation of neural fibers with 4 different diameters. You see that these are qualitatively be able to map the activity of the EMG muscle. And that's the result for another pattern, 954. You see that these are not as good as the previous one. So you see those performances. But we also see that the model can tell us the symmetric information. So there is a clear symmetry between the left and right, which we can also learn from this configuration. For this pattern 965, we see that, there are no EMG signal. Actually, although the stimulation is pretty strong, but there are no EMG response. And in our calculation, in our simulation, we also see very, very few response. There are almost no response for this pattern, which is a good thing. And this 998, we see strong response from the real EMG data, and we also see a strong response and in symmetry response from the calculated activation of neuron fibers. So those are the responses from the dorsal root. We also know that the stimulation is not only influencing the dorsal root, which is outside the cord. They're also influencing the fibers that within the white matter. So the fibers in white matter will also be activated by most of our stimulating parameters. So this makes things quite complicated. We need to take into consideration of basically all the spinal cord together with the dorsal roots and the ventral roots and all the possibilities. So this is very difficult. Okay, so how do we try to solve this problem? We try to map the fiber activation to their EMG activity using one neural network also in between. The input is the activation matrix of fibers in nerve roots and white matter, and the output is 12 channels of EMG signal. We use a neural network in between to describe the complicated mapping between the neural activity and muscle reaction. So here we actually have this full chain from a stimulating pattern to the possible neural responses in the dorsal roots and also in the white matter. And we go through a neural network to predict the results for the muscle activity, which could give us pretty good results. So now we can do some quantitative and qualitative and some quantitative understanding from stimulating patterns to our EMG behavior. Then how do we actually do the stimulation, the treatment in practice? How to stimulate? Okay, in practice, the configuration of stimulation is like a frequency with different frequency, with different spatial configuration. So it's a very huge stimulation configuration space. And what makes things difficult is that optimal stimulation varies among different patients. So our algorithmic problem, or the fundamental search, is a fundamental search and optimization problem over large action space or over large stimulating parameter space. The algorithmic foundation, which I won't talk into details, is the constraint optimization problem. Basically, we want to optimize the neural response subject to some safety constraints, which we don't violate the safety constraints, which could say harm the patient's feeling or others. And our first version of algorithm is a safe optimization, which is pretty much like a minesweeper. You see that if we don't do optimization carefully or properly, we end up at clicking to a mine, which ends the game or which ends the clinical treatments. But if you are a good minesweeper, you actually can gradually optimize and utilize the posterior to determine safe region and guarantee safety with high probability as this player. Our algorithm is actually performing in a similar way to choose stimulating parameters for patients. So here is the original reinforcement learning schedule for neuromodulation. We have the state space representing patients' motor activity and the action space representing the stimulating parameters. We apply optimization algorithm and achieve the control for standing. So this video shows you a bad standing, which is along the process of the optimization for good standing parameters. You see that this patient this is a fully paralyzed patient, can stand by himself, but cannot stand very well. He still needs the physician's help. And after some time of optimization, this patient can stand pretty well. He no longer need physicians to hold his knees or any part of the body, and he only used the standing frame for a bit balancing control. Nothing much. But that's not enough. Our new problem is focusing on from standing to walking. We want to do more activities and we want to be more efficient. So the new problem formulation need to be a more efficient one. So mathematically, we formulate as optimize a unknown reward function sequentially, subject to a unknown safety function, Gx. And here we call the decisions that satisfy this G greater or equal to H to be safe. And we hope to significantly improve the sample efficiency by just slightly losing the safety constraints. And in this sense, we give a probabilistic version of safety constraints like this. And we also use a encoder to map the huge stimulating parameter space into a lower dimensional one so that we can carry out optimistic safe optimization in a lower dimensional space. And the new optimistic safe algorithm solves a slightly different constraint optimization problem as following. Okay, so this basically compares the original safe optimization algorithm to the optimistic safe algorithm. So the new algorithm is more efficient on exploring and also with very few violations of safety. How does the whole new algorithmic procedure look like for our online treatments? To increase optimization efficiency, we optimistically estimate safe regions using upper confidence bound model by Gaussian processes. So our input stimulating parameter, together with the feedback signal from like the EMG, they were taken by the encoder, and those high dimensional signals were generated by the encoder to be going through the encoder and generate a low dimensional representation. And in the low dimensional representation space, we could do the optimistic safe optimization, as I just briefly described, the optimistic safe algorithm. And then for that optimization results, we could go through the decoder to generate a new input stimulating patterns. So this could go into a closed loop, that the new stimulating pattern going up to be the performing stimulating pattern and to collect feedbacks, to go through this process again and again. Okay, so how does the autoencoder part actually works? How do we represent the large input space into a small number, into a relatively small space? Our encoder is mapping hybrid high dimensional data to a low dimensional quasi-physical representation. And our decoder will map to the target output, which is some prior knowledge of the domain, some prior knowledge of the physical space. So in this part, we use one reconstruction loss, and considering the domain knowledge part, we add this domain knowledge integration loss. Also, to shape and regularize the whole shape of the stimulating parameter, we optimize the log likelihood of the Gaussian process with the process target knowledge and the code. So to adding those things together, we achieve this autoencoder part, which I previously shown in the whole pipeline of the closed loop optimization system. Okay, so then we go to the experiment part. How does this whole closed loop system work? In simulation, we show it works. And also, more importantly, in clinical experiments, we actually apply the algorithms to find good stimulating patterns. And we successfully achieve walking behavior for this fully motor complete spinal cord injured patient within a few months. So you show he was walking with the help of a standing frame in clinic and also in the outside the neighborhood area. And in the simulations, we actually sample random functions to making sure that this algorithm is performing well. It outperforms popular safe exploration algorithm with a large margin, and also it achieves comparable performance against the state-of-the-art algorithms. Now we go to the clinical experiments. For muscle selectivity experiments, we do the optimization of iliopsoas muscle selectivity. We achieve better performance compared to human experts. So here on this red line, you see that this algorithmic choice is gradually going upwards and achieving slightly better than human performance for the left iliopsoas muscle. And for the right, it also going above the human performance after a relatively small number of iterations. After single muscle optimization, we also applied for the optimization of standing capability of the patients. We achieved similar results, but the stimulating patterns, they are more diverse. We use multi-cathode solutions actually found by the optimistic safe algorithm. And these could imply more diffused electric fields, not so concentrated comparing to the human experts. And the more diffuse electric fields could potentially lead to better sustainability over time. And this plot shows, this video shows the clinical experiments of walking. So we, with the help of the algorithm and the human experts, we come up with spatial temporal stimulating patterns which could be able to restore the walking capability of the patients. And on the right is the control logic, which I won't talk into the each individual details. So here we could achieve relatively good walking behavior with pretty fast and efficient spatial temporal stimulation optimization. To sum up, we achieved modeling, designing, and optimization of the whole neural interface system and we do the implementation with the help of our clinical collaborators at the Tsinghua Chang'an Hospital, and we apply those therapies which successfully achieved good walking for these patients. So this video basically is showing that he go back home, and with the help of this standing frame, he can practice walk at home. Yeah, we know that he's still not walking perfectly well, and we're working very hard to achieve even better walking, standing, and moving capability for him in the future. Okay, with this, I'd like to thank you for your attention, and this is the joint work with Professor Lu Mingli and all the other amazing collaborators. Okay, thank you. All right, since I'm also the moderator of our section, I'll see if there are questions coming up from the audience. Oh, do I need to stop sharing? I guess I need to stop sharing before seeing things. Okay, let me see questions. Okay, so there is the one question saying that how to improve the involvement and engagement of human patients in the neurorehabilitation process. That's actually a good question for the rehabilitation parts. So this we know that spinal cord stimulation actually is not something like you take the medicine or you take the shock and everything's done. With the stimulation, the patient also need to do practice in order to achieve good motor capability. So there are actually some possible ways to design the training therapy, which could be more entertaining and more efficient for the patients. But still, the patient need to go through intensive training to achieve a good outcome against the gravity. In the end, we need to do exercise against the gravity in order to be able to stand and to walk. There is another question saying the exoskeleton and spinal cord stimulation both could recover locomotion capability, and how do you envision the two approaches in the future? Why do you deploy SCS instead of exoskeleton? Yes, I think that's a good point. We've seen using exoskeleton system for the training of those paralyzed patients. But we think that exoskeleton is something from the outside to the inside. You want to regularize the motion of each of your body parts. But the spinal cord stimulation thing is more from inside out. Is by directly stimulating your neural system in order to get good standing or good motor functions. So those two things are functionally, I think, from the mechanism, they're very different. But I think they are both very useful for the treatment of spinal cord for the treatment of spinal cord injury. Yeah. Okay, so condition on the time, and I also see our next speaker, Stanisa, he's ready. So condition on time, we're gonna stop this session for now and entering our session for the next speaker. Okay. Hi, Stanisa. So our next speaker is Professor Stanisa Raspopovic. So Stanisa Raspopovic has been since 2018 an assistant professor of neuroengineering at the Department of Health Science and Technology of the Swiss Federal Institute of Technology, Zurich. We call ETH Zurich in Switzerland. So his research interest is focused on the development of innovative medical devices for treatment of neurological disabled persons. In particular, he develops mechatronic systems directly interfacing the environment with the residual nervous system. Stanisa achieved the groundbreaking translational research results in the field of sensory restoration in amputee patients. By means of neuroprosthetic intervention, his group has shown that restoration of foot and knee sensations via neuroimplants in above-knee amputees diminish their pain, metabolic cost, and mental fatigue, while enhancing functionality, confidence, and acceptance of the processes. These man-machine efforts are now expanded to diabetes and stroke patients' treatments. Driven by the desire to share these inventions with a wider population, in 2014, he co-founded Sensar's neuroprosthesis, a spin-off that developed neuroprosthetic system, which won many international recognitions and raised several millions of non-dilutive funding. He won several grants from EU and Switzerland in the role of a project leader, and is presently the PI of the prestigious ERC starting grant Feel Again. All right, so with this introduction, let's welcome Professor Raspopovic, and welcome.
Thank you. Very nice to hear and meet you. It's a big pleasure and a big honor to be here. I hope you can see my screen here.
Yes, we can see it.
Yeah.
The full screen.
So, in the next 25 minutes approximately, I'm going to guide you through our developments as anticipated in how do we connect the machines and nervous system for the means of neurorehabilitation. And I'm really glad to take any of your questions at the end. So in my lab, we are working in a framework which is departing from a basic science. So we work on animal and modeling, in silico modeling experiments, in order to understand better how the touch and multisensory integration work on a peripheral and central nervous system level. Then we implement those findings within the computational models where we are learning how the nerves are communicated to each other, so more in particular, through which language they speak, and how we should communicate with them through our artificial means. The next thing where we are implementing this knowledge, and I'm doing a lot of research there, but today, unfortunately, the time frame is not enabling me to explain it, is about the chronic pain, where we are developing, based on those in silico models, where we implement the pain signaling, we are making a digital solution for chronic pain. And then those are connected to our main effort, which is in bioelectronic medicine, which we use through the implantable devices for the treatment of diabetes and neuropathy, for the sensory motor assistant in human machine, as we could see in a previous stroke, also regarding the diseases of the central nervous system. And last but not the least, and today's talk is mainly going to be focused on that, is about restoring artificially somatosensation through the sensory restoration via implants. So, what are the specific challenges in this multidisciplinary research field? So we have amputees and diabetics that have several unmet needs, as it is low mobility, as you're going to see in 1 second from now. They are falling, so they're experiencing very dangerous falls. Due to the fact that they are having increased metabolic costs, they are 200% more prone than us to have a heart attack. And then many of amputees and diabetic patients are experiencing the neuropathic pain. And even though the modern prostheses are just half of the weight of our legs, they are experiencing a prosthesis as being much higher weight than their normal leg. How do we try to treat those problems? We communicate with the nervous system. And more in particular, in my research, we're speaking to the peripheral nervous system, as you can see in this schematic. And so to do so, we have to understand which type of device we have to use and how to speak to nerves. So where and what to implant and how to inject the current to the nervous system. That is the science behind. Once when we learn that, we can jump into the neurotech solution. And this is what we are doing. We are connecting the sensors, the system communications, and implantable and non-implantable devices in order to transmit the information from the external world to the patients. To do so, we must understand the surgical and technological viability of those. And then at the end, we can use these devices for the restoration of the lost sensory and motor function and or for the pain management. So how is that translated into my research philosophy? So we are starting from the basics. So we are first learning deep understanding of a system we try to work with. So as you can see here, these are the realistic histologies for the human samples. So we start from those realistic histologies of particular nervous structure. So in this case is the lower leg, sciatic and tibial nerve. And we then construct the 3D realistic computational models in which we are able to manipulate the current in a way to stimulate an artificial axonal population, and so to understand in this infinite space which electrodes and where should be implemented in order to stimulate more selectively. Then, starting from them, we do develop devices. So this is an example of our sensory leg in which we make the sensorized insoles, we produce the system controller, and then we connect that to the residual nervous system. And very importantly, then we go into the clinical validation. So we do assessments. We work a lot into the movement analysis and to the metabolic and dynamic analysis of the human behavior during the walking. But just in this moment, and this very end of this process is the most important step for the scientific advancement, is when we learn from our clinical assessment what were the wrong hypotheses in our starting basic understanding, we return back and we correct our models. And only in this way we are able to earn more and more knowledge about the systems we are trying to stimulate or communicate with, and really to progress the science and therefore the neurorehabilitation of the users. So let's start with examples. As promised, there are amputees. So why is haptic feedback so crucial? So in these videos, on both sides, you can see the patient on the right, which is a sensorized, which has the anesthetized finger, and on the left you see the normally loaded sensory feedback. So on the left, the person who was able to stitch the measures immediately and to make the fire, and on the right, she's yet trying to do it after me speaking half a minute, and this is only due to the fact that she's temporarily not having the sensory feedback, the touch feedback. And this is a classical Johansson experiment in which we can understand, really quantified in seconds, why sensory feedback important in sensory motor control. So when we go more into the details about amputees, once that you're amputated, you have several possibilities. So first possibility is you're lucky enough to have the amputation close to the modern clinical center, that is reimplantation, in which cutted part of the body is being replaced back to the body through the surgical intervention of the multidisciplinary surgeon team, in which they are the guys working with the grafts of the nerves, of the blood vessels, or on the skin, and then we can have the amputated limb connected back to the body. But unfortunately, if that happens in some jungle very far away from such a center, or if the amputated part is destroyed as for the burning, nothing can be done with reimplantation. In 80s, very promising solution via a transplantation from cadavers appeared in France, and after the initial waves of optimism, unfortunately today that option is not widely recognize the best one because of the two reasons. First is that those persons need immunosuppressors for the lifelong. Therefore, it means that they, after a while, have problems with other organs like kidneys. And very often underestimated problem is the psychological problem. They would state that other persons, like their beloved persons, feel a psychological moment when they are being touched from the part of the body of the dead persons. And so even that is not a solution. And some years ago, in the Rehabilitation Institute of Chicago, very interesting solution for especially proximal amputees appeared, which is called the muscular reinnervation. It means that through the surgical intervention, the residual nerves post-amputations are being extended and reimplanted into the residual muscles. Then those would grow into these muscles, and whenever the user would, for instance, imagine to move some part of the fingers, the chest muscles going to move, and we can record that superficial activity and move the prosthetic device. Not only when you touch that area which is reinnervated, the users are able to feel the missing leg, arm, for instance. But the problem is here that it is very difficult to control the same muscle while contracting it and to feel the touch over it. That's a sensory gating issue. And so recently, both on direct muscular interfacing, those small, white, tiny things are muscular implants that are being developed in the United States and now used also from Osher company, are being able to send the residual muscular signal one-to-one to the system and to drive the motor of the prosthetic device. On the other side, it is possible to make a direct nerve interfacing, so we can go around or through the nerves, and you can see it in a picture on the left, and stimulate those residual nerves, and the users are going to feel the sensation of the missing arm. And finally, if we combine those, we're going to have a bionic solution. This is where I work a lot. So to be able to control the device effortlessly and to feel while doing that. And that's a real goal of intuitive and complete neurorehabilitation. So the first question I promise you to address is how to speak to the nerves. To answer this question, we in my group, together with the collaborators in Sheffield and in Canada, we developed a model, foot-STEAM model, in which we are able, through the appropriate tuning, to understand the behavior of 4 different classes of mechanoreceptor existing in the foot sole and to model their behavior in real time to the mathematical and computational ways. To do so, we start from understanding the hardness of different areas of the foot sole, and then we do experiments. So we with the robot, we are pressing over different areas of the foot sole. That's the collaborators from Canada that did that, and they provided us with the data of the response of singular afferent fibers. And then we were able to fine-tune our model and to understand that in reality, we are doing quite well, and that we are able to replicate the behavior of 4 different classes of afferents. Then, starting from that, we developed the artificial mechanical stimulus, and we were able to understand, to estimate how would different classes of fibers spike while doing so. And then we can use that for an artificial system in which we would code the neurostimulator behavior based on that. To prove that those findings, we could make a very challenging experimental setup with cat model in which we implanted a peripheral nerve and also dorsal root ganglion and finally spinal cord. And we were able to understand that when doing so, when injecting those biomimetic neural signals, those information are traveling quite properly through the spinal cord until the higher levels of the brain. So in the first place, we are able to understand how to stimulate, so how to speak to the nerves. Then the second question is, which device to implant and where to implant it. And to address this question, you use a different class of models, which are called the hybrid computational models, FEM neuron models, in which we start from the realistic histologies from the FEM model, in which we segmentate the nerve structures and radially extend them in order to understand the behavior of electric fields without a model, and then we connect that to the behavior of in silico models, so the axons which are artificially implanted within the areas, and then when we modulate the positioning of electrodes that are injecting the current to the nervous system, we are able to understand which is an appropriate positioning of the electrode or type of electrode to use. And then generalizing this approach, which we generalize both for the upper and lower limb, we are able to fine-tune the dimensions of electrodes, the shape of active sites, and their number of implants. And so from these things, we were able, for instance, to answer the typical question we got from surgeons, which is how many implants should be implanted in a specific nerve. So we can implant virtually the 1 electrode, 2 electrodes, or even 3 electrodes. And then we can understand that, for instance, the 3rd electrode is too much for this specific ulnar nerve, and we are able to have a really high selectivity with 2 of them. So it's a nice simulation in a computer, but when this is used in reality, this is what we have. We have the real behavior of our implants, so we are able to understand and implant in a way that we projected through our models. And this is what we in reality did. So we have this sensory neuroprosthetic solution. So this is the way that amputees walk. They are slow and asymmetric. So we instrumented the prosthetic device with a sensorized insole and an encoder in the knee, which in real time are transmitting these sensors information to the brain of the system, which is capturing the information and then transmitting it into the side nerves through these designed electrodes, which we did through the models, and through the language that we learned through our modeling. And then the nature does the rest. The signal is conveyed from the peripheral nerve to the spinal cord until the higher structure in the brain, and the users are feeling they're walking as with their clothes as with their natural leg, being therefore more confident and being able to walk in a more proper way, more healthy way. So it's a nice simulation and animation, but then we jumped also into the reality. We were able to engage at least 3 subjects with a bony amputation, with a strong phantom pain and fear and feeling. That was a big pan-European effort, including several research and industrial activities. And we performed a quite long-term clinical testing on 100 days in order to understand what are pros and cons of this neuro implant approach. So what is the first step? A few days after implant, we were able to restore the dormant sensation. So these are what you can see in the maps are the parts of the missing fit of those users. These are 3 subjects, so different colors are corresponding to the different active sites of different electrodes implanted, which they would refer as feeling. So I would inject the current for the single active site within the nerve, and they would say, okay, I feel the big toe, for instance. Similarly, they were also feeling the lower leg, so the areas that you can see in A, B, C, D, and those were quite repeatable. Those sensations of different type in which predominance was a pleasant sensation close to touch were able to be elicited properly and repeatedly in all of 3 subjects. And then when a little bit of engineering is applied, this is what happens. So this is a placebo trial, for instance. I'm not touching anything, and the user is indeed reporting that he doesn't feel anything. And then whenever I was touching the different areas of the sensorized insole, you can see there, they are wirelessly transmitted to the green box until the system controller, which is close to the white box on the table. And then we are transcutaneously stimulating the residual nerves. And the user is feeling precisely the same position within the foot that he's not having anymore. And then the similar thing was possible to be done also with the flexion of the knee, during which we were able to encode the knee closure with respect on the areas A, B, C, D, and specifically with respect to gastrocnemius medialis. And then we can combine both of them. They can feel the proprioception and the touch together. And hopefully, as a next step, use those and exploit those during the functional tasks. And indeed, the very challenging task for our users is stair mobility. So they are fatiguing a lot. They don't feel a confidence while doing it. And here in the video, you can see the difference of situation where the neuroprosthesis is on and when we are not injecting the current into the nervous system. So due to the fact that we are properly restoring the neurophysiological situation, they have more confidence, and therefore they are able to push strongly and more quicker their leg. Therefore, to increase their mobility. And the mobility is the first determinant factor both for the health and for the reinsertion into the healthy society of those disabled patients. When this has been quantified on the left, we could observe that in all patients, through the neurointegrated sensory feedback, we were able to achieve much bigger and better mobility. In a next set of experiments which are above, we were making those users to walk over obstacles while having the glasses which disabled their sight over the obstacles. And when they were neurointegrated with the sensory feedback, they could fall less and have better mobility over those obstacles with respect to the situation in which they were having the commercial prosthesis. Not only when after those tasks, we tested their perception of the prosthesis and the weight of the prosthesis, we could observe through the psychosomatic measures that they felt prosthesis as a 1/4 less heavy when they were having a sensory feedback with respect to the situation in which they were using a commercial prosthesis. And one of the reasons why there was that is because they were feeling prosthesis as more as a part of their body, as we have measured through the quantitative embodiment measures. Not only, we ask ourselves also what was happening on their brain level. So first we measured the functional embodiment. And so in that experiment, those pool that you can see on the left, they would say when they feel their missing fit aligned with that pool. And so we could understand that they were feeling the pool more aligned with their missing foot when they were receiving the sensory stimulation. So their proprioceptive drift was smaller and their embodiment was higher. And finally, we also measured via EEG their behavior while having a sensory feedback. So we asked them to count in a double task the terms of the different height and to walk or to sit. So what happened is while they were sitting and counting the tones or walking with the sensory feedback and counting the tones, their residual ERP mental layover was high. So they could also answer you about which is the capital city of China. While when they were just walking and calculating those tones, counting these tones without sensory feedback, their mental layover was very slow, very low. So they could not answer any questions. So they were really concentrated on that task. And we do believe that this cognitive ease is one of the reasons why this successful prosthetic application. And so we also had a very relevant clinical outcome. So when we measured their phantom limb pain during the implant, we could observe that it was quite diminished up to almost zero level with respect to a day of implantation. And most importantly, after 100 days and their explant, the pain was returning. It means that most probably this pain reduction was not due only to the surgical intervention, but was really due to the specific neuromodulation that we were providing. Also, as promised, metabolic cost, that is a very big problem. We have observed that when they were using the sensory device, giving them more symmetry was quite statistically diminished, which is a big promise to diminishing heart attacks in those patients. Then, of course, we ask ourselves, why is this happening? And so we studied quite in detail the kinematics and dynamics of those users while walking with the sensory feedback. And without too many details, what happens is that we were reshaping their walking ability more towards the physiological walk. So they're really stepping from back of the foot up till front of the foot, and they're exploiting this artificial sensory information in a proper way to reshape their walking. And this is most probably the reason of all the benefits that I've been mentioning. As promised, after experiments, this is the line that is really important to push the science forward. We ask ourselves what was bad together with all of these good results. And to understand that, we collected many of clinical trials done worldwide with almost 100 patients in the upper and lower limb. And we have learned what are the problems of different devices and behaviors. To summarize it, the problem is the type of sensation. Many of the sensations we elicit or everybody elicit are often close to the electricity. And that is often underestimated also in the spinal cord implants, but that's unpleasant for the users. So we work hard to diminish the number of unpleasant sensations. Also, as in our clinical trial, in many others, the problem is the lack of the reliable implantable pulse generator. So majority of these studies is done through the transcutaneous cables, which are problematic from surgical and maintenance viewpoint, because then users cannot be really relaxed and use it fully. They have to take a lot of care. So we have to solve these problems to push the science forward and to make really reliable and repeatable implantation techniques. As promised, then we made, a version of this system which is usable already today that doesn't need implants. And to do so, we implemented a system that has been really carefully studied together with a multifaceted analysis, the GRAIL system and YCON, in which we were eliciting the sensation through the transcutaneous stimulation of our users. And through this stimulation over skin, the results were not as detailed as with implantable, but they enabled users to have the reliable everyday activities, which they were able to exploit, for instance, during the cyclothlon of the last year. So you can see this picture. Our user, he's a manager, and he's doing this, not the sport field, not the Paralympic, but doing this quite difficult task. And in reality, he took a silver medal in front of Paralympic champion from Iceland. And as I promised, just to make a consequence on our new projects, diabetes have similar important issues. So diabetes is a very complicated disease in which, as a consequence of metabolic processes, the persons are using protective pain. So they do not feel under their foot sole. So even a small rock in a shoe can make a personal and long-term damage. And this can go to the ulcer formation, which is a big problem because big number of ulcers are finishing in amputation, which is unfortunately finishing in many deaths. At the same time, those users are feeling a phantom limb pain. So they're reporting similar things as a phantom limb pain. It's a neuropathic pain of a similar type. And they're feeling a pain which preserves them from doing the normal everyday activities. And this is the way they walk, for instance. So it's very unstable, very slow walking, and they often in advanced stages of disease, they need assistance while walking, as you can see in this video. And so we are working on that. We are translating our system into the multimodal treatment. So in one of applications that we are working with, which is translating that into neuroprosthesis, we are combining the virtual reality and sensory stimulation through the skin. So the users are really feeling what they see on a screen. And long story very short, this is what they are doing. So, and the video is probably here. Yeah. So they are in this Swiss river, and they are seeing what you can see on the left, and they're trying to collect those coins while avoiding while avoiding the cans. And at the same time, we are stimulating somatotopically. So we are using what we believe is very important, the intuitiveness of sensation, and we are training their nervous system in order to increase the mobility and decrease the pain. So in a conclusion, we developed the neurotech system for a system of assistance and health in disabled. And we are using the hypothesis-driven modeling approach respect to the brute force trial and error. And to do so, we did from in vivo experiments to in silico receptors and nerves, which were then used for the physiologically plausible conveying of sensation to the human body, which enabled us to make a unique translational discoveries with less pain, more confidence, higher mobility, and which on the long run, I believe, will make a healthier life and social reintegration. And all of that is really useful and important for the neurorehabilitation, for the healthy aging, and at the end, the meaningful life of those users. And last but not the least, we work a lot hardly to restore the functionality. But it is important to remember that the happiness of users and us is very essential.
Okay, man.
And with that, I have really to thank a multiple team. All the merits are those beautiful persons that work with me on this experimental and computational model and engineering and on a clinical test, together with my external collaborators for animal and technological developments. And with this, this is my group, the different funding models that helped us generously. And I'm more than happy to take any of your questions.
All right. Thank you, Stanisa, for this great talk, really bridging the cutting-edge engineering to the neuroprosthesis. So we'll start with a question from the audience. This is the focusing on the long-term effects. So, Professor Raspopovic, what would be the long-term effects of such a smart human-machine interface to the central and peripheral nervous system?
That is really an excellent question. So, of course, we were working on that, and I will summarize a very complex answer in very few points. First, the question is, what is the histological effect? We have studied that. We have studied rats up to 6 months, which correspond to multiple years in humans, and the effects on the peripheral nervous systems were really mild. So it means there is a neurointegration of the devices through the fibrotic encapsulations, and we can stimulate over multiple years, theoretically and physically many. So there are experiments in Sweden stimulating over 8 years. While on the peripheral and central nervous system, we can only make a hypothesis. And my belief is that those results that we see in 3 or 6 months are going to be even better in the long run, because users are going to learn perfectly those artificial sensations and going to exploit those both for the functional but also psychological recovery. They're going to really rely on that part of their regained nervous system. But of course, it must be tested on a long run a posteriori in order to say it. Last but not the least, I think there are multiple efforts in the world which are going into the same direction and are cross-fertilizing. And very soon we are going to have a really reliable answer on this very good question.
I see. So in terms of long-term effect, you're actually quite optimistic about the...
technologically based, we are optimistic because the technology is very similar as the one used for the other neurotechnologies. Functionally wise, it must be demonstrated, but it doesn't make sense. It makes sense that it will work in a similar way.
Mm-hmm. Yep. So, constrained on the time, we'll have another question to be the last one. So, is it available that the patient's central nervous system understand and react to this artificial stimulation language directly without translation, or the cerebral cortex has to learn and translate it from the entire nervous system?
Oh, that's very nice question. Our approach, so there are different approaches. Our approach is that users, we implement the stimulation that is as intuitive as possible. And so the users so I have that video after 3 hours post stimulation, the user will just feel, I feel back foot, I feel forefoot, and I feel like somebody pressing me underfoot sole. So we are not making in a way that they must interpret. And our approach, I do believe that patients would not easily accept the system that they need to train. In reality, that has been demonstrated, because when you try to train the users with non-intuitive system, they're often unhappy to use them. So in our case, the cortex doesn't need to learn so much, while when stimulating directly in the cortex, the situation is a little bit different. And there are many efforts, for instance, in Pittsburgh, trying to understand that better.
All right. So thank you very much, Stanisa. And with this, we'll end your session. And thank you very much.
Thank you for this great opportunity and for your kindness.
Yep. All right. So our next speaker is Professor Yijun Wang. Dr. Yijun Wang, he's a research fellow at the Institute of Semiconductors, Chinese Academy of Sciences. He's a member of CAS Center for Excellence in Brain Science and Intelligence Technology and the CABR Scholar of Chinese Institute for Brain Research, Beijing. He received a bachelor degree and a PhD degree in biomedical engineering from Tsinghua University. And from 2008 to 2015, he was first a postdoc fellow and later assistant project scientist at the Institute for Neurocomputation, University of California, San Diego, in the United States. His research mainly focused on neuroengineering and neurocomputation. His research interests include brain-computer interface, biomedical signal processing, and machine learning. He has published more than 100 papers in scientific journals such as PNAS, Journal of Neuroscience, IEEE Transactions on biomedical engineering. His paper have been cited more than 9,000 times according to Google Scholar with a niche index of 48. With this, let's welcome Professor Yijun Wang.
Okay, thanks a lot for Professor Sui's introduction. And so, shall I share my screen now?
Yes, please.
Okay. So, does it work?
Yes, we can see your screen.
Okay.
Yeah, now the full screen mode.
Okay, so good afternoon, everybody. I'm Yijun Wang from Institute of Semiconductors, Chinese Academy of Sciences. And first, thanks for Professor Li and Professor Sui's invitation. So I'm very glad to have this opportunity at Beijing Brain Conference to talk about our work on high-speed brain-computer interface based on visual evoked potentials. Here is the outline. I will first give a very brief introduction of the research background. And next, I will focus on the fundamentals of BEP-based BCI. And then the two major components, stimulus coding and EEG decoding of BEP-based BCI. And in the end, I will also show some examples of potential applications of the BEP-based BCI. Okay, so let's start with the background. So we all know like brain-computer interface provides a direct communication channel between human brain and the output devices. It does not depend on traditional output pathways of peripheral nerves and muscles. So the original purpose of BCI research is to help patients with motor disabilities to communicate with their environments. So as shown in this figure, a typical BCI system consists of the three major components: signal acquisition, signal processing, and device control. So in today's talk, I will focus on non-invasive BCI based on EEG signals, which is the most popular method in current BCI research. The applications of EEG-based BCI can be categorized into three groups, including communication and control, rehabilitation and augmentation, and brain state monitoring. So my work is majorly focused on the communication and control purpose. During the past several decades, three types of EEG signals have become the most popular used EEG signal in BCI: the steady-state visual evoked potentials, the P300 evoked potentials, and the sensory motor mu and beta rhythms. So my work majorly focused on the BCI based on the steady-state visual evoked potentials, which has the advantage of high information transfer rate, and it requires very little user training, so it's appropriate for the communication and control purpose. Okay, now let's go to the fundamentals of BEP-based BCI first. So visual evoked potentials are changes in EEG potential produced by the visual cortex of the brain in response to the external visual stimuli. The visual stimuli could be like flashes of lights or graphic stimuli. Depending on the temporal property of visual stimuli, VEP can be categorized into transient VEP and steady-state VEP. Steady-state VEP is the brain's response to repetitive visual stimuli, a periodic flickering signal. SSVEP is also called photic driving responses. So the most prominent character of SSVEP is that the fundamental frequency of SSVEP is the same as the frequency of the stimulus. SSVEP can be recorded in the occipital area with the highest amplitude and signal to noise ratio on the scalp. Another property of SSVEP is the mechanism of cortical magnification. According to the central magnification effect of visual cortex, the stimulus in the central visual field will cause significantly increase the SSVEP. Therefore, it's possible to detect the stimulus in the central visual field by detecting the SSVEP signal. So a multi-target BCI can be realized based on photic driving character and the cortical magnification effect. The user can select a target just by directly looking at it. So this is the basic principle of the SSVEP-based BCI. This figure shows a typical frequency coding diagram. We can see like a virtual keypad was realized by labeling each key with a different stimulus frequency. For example, 13 Hertz and 15 Hertz were used to tag these two keys. So the target key the user is fixating at can be identified by detecting the dominant frequency of SSVEP signal. By detecting visual evoked potentials by target stimulus from a visual stimulator, VEP BCI can convert users' intention into control commands, and thereby establishing a direct communication between brain and output devices. For performance evaluation, the information transfer rate bits per minute has been widely used. The ITR depends on three parameters: the number of classes and classification accuracy P, and the time for each command selection T. For SSVEP BCI, we published in 2015, the ITR can reach to 270 bits per minute, leading to a typing speed of 1 character per second. The VEP-based BCI can be considered as a communication system, which consists of a modulation component and a demodulation component. The modulation of EEG is realized by stimulus coding, and the demodulation is performed through EEG decoding. So in modulation, the multiple target coding approaches from telecommunications can be applied to modulate SSVEP signals towards a large number of targets. Okay, now I will introduce our work on stimulus coding in VEP-based BCI. The multiple access technology in wireless communication has been systematically introduced to facilitate the design and implementation of BCI. The commonly used multiple access methods include time division, frequency division, code division, space division, and hybrid multiple access methods. In stimulus coding of SSVEP, the stimulation frequency plays a very important role in optimizing the amplitude response and user experience. Low frequency around 10 Hertz in the alpha frequency range actually shows the highest amplitude and signal-to-noise ratio. This frequency range has been widely used in BCI towards high information transfer rate because the SNR is the highest in this frequency range. However, in this range, the comfort level is the worst. So recently, we found out that the lower frequency range below 5 Hertz and the high frequency range above 40 Hertz show much better user experience. In the low frequency range, we proposed a joint frequency phase modulation method towards the highest information transfer rate in BCI. we use the joint frequency phase modulation to improve the coding efficiency. So we can see like the frequency range is from 8 Hertz to 15.8 Hertz, and the frequency interval is only 0.2 Hertz, and the phase interval is 0.35 pi. A high-speed BCI, speller used in this 40 target scheme, can reach the speed of 1 character per second. So in this video, we can see that the user is using the system to type high-speed BCI at a speed of 1 character per second. Towards better user experience, the 40 target BCI paradigm was also extended to the high frequency range at 55 Hertz to 62.8 Hertz, which is near the critical fusion frequency. So the system can realize visual stimulation near the sense of the flicker. This video shows the real-time operation of the high frequency BCI. We can see like the stimulation paradigm is much more comfortable to use than the low frequency stimulation. For the code division multiple access method, a cyclic shift of an M sequence can be used for multiple stimulus coding. The code modulation visual evoked potential paradigm can reduce the calibration time and increase the number of targets. In one of our recent studies, we developed a BCI system with 120 targets by combining 4 different M sequences. For the space division method, we developed a personalized spatial coding method. Different locations in the visual field can be mapped to different brain areas in the visual cortex according to the retinal topic mapping. Because the brain sources show different orientations in the visual cortex, the mixture of different SSVP components may cause the canceling out effect, leading to a very serious attenuation of SSVP signals. So to compensate the phase difference, we used phase coding in each sector to enhance the SSVP response of the whole ring stimulus for each different subjects. So this method has been successfully used to implement a full-class BCI using stimuli at 60 Hertz. We can see in a demo video that's like imperceptible 60 Hertz stimulus for 4 different phase-coded targets. To further optimize the user experience, the mechanism of the visual on-off system was introduced into stimulation design. We propose a new grid stimulus to present the on-type, off-type, on-off type stimuli and compare them to the traditional flicker. Different spatial contrasts were also compared in terms of user experience and classification performance. We can see the off-type stimulus shows a good balance between user experience and classification accuracy. This video shows the 4 types of stimuli under different contrasts. We can see that the off-type and on-type stimuli are much more comfortable to use than the traditional flicker. Okay, so we just went through the studies of the stimulus coding, and now let's look at the EEG decoding algorithms for VEP detection. This figure summarizes the evolution of the most widely used approaches in VEP BCI. The algorithms developed by our team and our collaborators are highlighted in red. We can see like the power spectrum density analysis method was a very early method, which is easy to use. And then the CCA, the canonical correlation analysis method and its extension approaches can enhance the SNR of multi-channel EEG signals. And the TRCA and the TDCA algorithms further improve the spatial filters. So these methods have been very widely used in current BCI research. And I will introduce some of them with details in the next several slides. The first algorithm is a canonical correlation analysis, which was employed to design spatial filters for enhance the SNR of SSVEP. So the basic principle is to maximize the correlation between SSVEP and the predefined reference signals. CCA algorithm can find the linear combination coefficients WX and WY which gives the largest correlation between projected X and Y. Because the reference signals are sinusoidal sine and cosine signals at the stimulation frequency. So CCA is an unsupervised method for SSVP detection. And based on CCA and by replacing the sinusoidal reference signal with individual EEG templates, the detection performance can be significantly improved. Here, the goal of CCA is then to maximize the correlation between SSVP and the individual EEG templates. So the individual templates can be obtained from a training session, which is required in system calibration. And then the correlation between a new testing trial and all training templates can be computed. The class of the template corresponding to the largest correlation is determined as the target frequency. Another highly efficient strategy in SSVP detection is the filter bank analysis method. So according to the characteristic frequency responses at fundamental and harmonic frequencies of SSVP, the filter bank analysis can extract independent information from harmonic components. So we can see like feature extraction is performed with all subband signals, and the extracted features are combined together by a weighted ensemble classifier. So in data analysis, the use of 7 subbands can achieve the highest classification accuracy in the 40-class BCI. Task-related component analysis is the method that extracts task-related components very efficiently by maximizing the reproducibility during the task periods. We first introduced TRCA into SSVP detection and proposed a new ensemble TRCA algorithm to fuse information from multiple spatial filters. The combination of TRCA and the joint frequency phase modulation method led to the highest information transfer rate of 325 bits per minute, leading to a typing speed of 800 milliseconds per character. Recently, we developed a new task discriminant component analysis approach towards the classification task in SSVP. So compared to TRCA, which obtain multiple spatial filters for multiple classes, TDCA fused multiple class task spatial filters, and a more efficient spatial filter can be obtained to improve the accuracy in SSVP detection. TDCA algorithm has been proved highly efficient by validation with multiple data sets. For supervised algorithms, they always require calibration due to the non-stationarity of EEG signals. So the difficulty in zero training algorithms always remain a big challenge in SSVP BCI. And we developed the transfer learning algorithms to reduce the calibration time. The alpha algorithm based on subspace decomposition and alignment has been proposed towards the training-free detection of SSVP. In 2 conditions, like including cross-electrode condition and cross-state condition, the alpha algorithm actually achieves BCI performance comparable to the condition with the within-session calibration. So this progress makes it possible to implement a plug-and-play BCI system with very high communication speed. In the study of SSVP decoding, we collected multiple open datasets for SSVP-based BCI, and we organized the BCI brain-controlled robot contest in the World Robot Contest, and published the high-quality datasets, including the benchmark dataset, application system dataset, wearable system dataset, and aging population dataset. These open datasets are very helpful and useful for developing and validating new algorithms in SSVP detection. Okay, so next, I will show some examples of potential applications with the SSVP-based BCI. By optimizing BCI performance and user experience, we developed various demonstrations of VEP-based BCI towards practical applications. The examples including like the BCI speller and the BCI for wheelchair control and for smart home living equipment control, and other examples such as like gaming and brain state monitoring. And so the first example I will show here is the design of a brain switch, which is simple but very useful for BCI. The code-modulated VEP signals based synchronous brain switches with automatic idle state detection were implemented with a sliding window detection algorithm. So these two videos shows single target and multi-target paradigms. The system can switch to different command states very fast by just directly looking at the target stimuli. The decision can be made like within 1 to 2 seconds. More importantly, when the user is in the idle state, the state of the system can remain unchanged without false positive. This is very important. So the synchronized BCI system is much more convenient to use than the synchronous BCI paradigms. The second example is to use the BCI to design a Chinese BCI speller for an ALS patient. Here, the lock-in patient shown here used the system to type Chinese characters, and the system further can convert the text to speech to help him to talk with other people. So this video shows an online demonstration of the application in a TV show. We can see like the lock-in patient can use the pinyin input method to type Chinese characters. And the accuracy actually is pretty high in such a noisy environment. And this figure shows we tested the whole system in his home condition, and the subject actually is satisfied with the performance of the system. He always used like an eye tracking system in his daily life, but with the BCI system, he can currently he can go to like a comparable performance to the eye tracking system he used. The high-speed BCI scheme used in visual stimulus encoding and EEG decoding has realized a variety of BCI systems with more than 100 targets. Here I show 3 examples of the systems we developed. The first is 108 target BCI by combining SSVP signal and P300 signal. The second system used is a 120 target system by combining code-modulated VEP signals. And the third example is the 160 target BCI by sequential coding of SSVEP. So we can see here in this demo using the 120 target BCI, the maximum speed of the Chinese typing system reached 20 words per minute, and the maximum information transfer rate reached to 400 bits per minute. So here the subject is using the system to type Beijing is the capital of China by a pinyin input method. And we designed the 120 target virtual keypad to help him to type very fast with the association function. And the third example is to use the BCI to control the robotic arms. For the direct control paradigm, we designed a BCI system with 3 types of commands for translation, rotation, and gripper control. And for the hybrid control paradigms, computer vision and VR, AR headsets were integrated with BCI for the more efficient control. BCI selects the predefined tasks, and then the robotic arm can perform the reaching and grasping tasks by computer vision. And in this demonstrations, we can see like we use a wearable wireless EEG system to implement the wearable BCI systems. This example is towards more generalized HCI applications, the human-computer interaction conditions. And we develop wearable BCI systems for different HCI tasks. These demonstrations include the game control task and the video playback task and telephone dialing and text input. We adopted different types of stimuli, like due to different number of targets and the different requirements for user experience. So adopt different types of stimuli to balance the BCI performance and the user experience. Okay, so different from the previous demonstrations towards the communication and the control purpose, the last two examples actually are different. The example is we developed an EEG-based biometric system using visual evoked potentials. So EEG-based biometrics has the higher level of safety and security compared to the other biometric methods such as fingerprints and face recognition. It has several advantages. For example, EEG-based biometrics is difficult to fabricate, and it can't be stolen, and it always requires living identification. So the framework of the VEP-based BCI was introduced to the design of the EEG-based biometric system to achieve the high precision and fast identification. So as shown in this demo video, we can see with data length less than 10 seconds, correct recognition rate can reach 98.93%, and with an average day interval of 200 days. So this results demonstrates the feasibility of visual evoked potentials for individual identification in practical applications. And the last example here is a portable BCI platform for visual field test. We employed the frequency coding approach to encode the visual field with 20 sectors and present the stimulus to a patient using a VR headset, which combines a portable EEG recording system. The SSVP signal corresponding to the visual field defects show significantly lower amplitude and lower stability. So in this way, the system can monitor the progression of the visual field loss for glaucoma patients, and they can use the system very often at home. Okay, so that's all for my talk today. So at the end, I would like to thank all my team members at Chinese Academy of Sciences and the collaborators at Tsinghua University, Chinese Academy of Medical Sciences, and University of California, San Diego. Our research has been supported by multiple research grants from China. And thank you very much for your attention. I will be very happy to answer any question. Thank you.
All right. Thank you, Professor Wang, for this interesting talk on visual brain-machine interface, brain-computer interface. So the first question from the audience is asked, hi, Professor Wang. We see the gradually increasing bandpath for this visual-based BCI. Is there a speed limit for non-invasive visual-based BCI?
Okay, so this is a very good question. And actually, according to the Shannon theory, because we always consider the BCI system as a communication system, so the limit of bandwidth can be estimated. And currently, I just mentioned that the current ITR for the SSD BCI is around 300 bits per minute. But if you use like the Shannon equation to calculate, it's about like maybe like 10 times as the current speed. So the speed limit can be calculated according to two parameters. The first is the bandwidth of the brain signal, because the non-invasive EEG signal actually has a pretty low bandwidth. We can only use like 30 hertz the bandwidth to code the stimulus. But if we use, if we can extend the bandwidth to a little bit higher, as I mentioned in my talk, we can use like the 60 hertz stimulus, and then the bandwidth can be improved a lot. The second parameter actually is the signal to noise ratio. there are a lot of methods, including not only like the algorithms, but also like the electors or like recording systems, and also including like different modalities such as EEG combined with MEG signals. And then we can improve the speed of current BCI in next maybe 5 to 10 years. We expect to go like multiple times higher than current speed. Thank you.
I see. Yeah. So and there is another question. I guess probably who asked this question also asked a similar question to Professor Edward Chang previously. The question is that so is there a possibility to directly do the brain-computer interface via decoding the characters and the words imagined by the subjects, instead of doing the visual-based approach by EEG?
Okay, so currently, I mean, like for imagination paradigm, it's very difficult to decode like multiple different classes. So in my opinion, because we currently use like the stimulation-based paradigm, right, to evoke the stimulus, and then we can decode like the very like straightforward the characters, for example, like the frequency or like the different phase and other like parameters. So if you want to use like imagination to decode like the very abstract concepts for a scalp EEG, I think it's very, very difficult. So we are waiting for like some breakthrough in this field, like in neuroscience, to know how EEG can decode this information. Yeah, but if we can get like more details or more other like algorithms to decode this information, it will be possible. But currently in this field, we are still like waiting for like new algorithms or new theories to do this. Okay, that's my understanding.
I see. Yeah, thank you, Professor Wang. With the condition of time, we will end this session with Professor Wang and entering our next session with Professor Kendall Lee. So, Professor Lee. Yeah. Okay, and our next speaker is Professor Kendall Lee from Mayo Clinic. Let me first have a brief intro of Professor Kendall Lee. Yeah, I think he's online now.
Yes,
Kendall,
can you hear me? Okay.
Yes, I can hear you. I'll first great you make it, and I'll first have a quick intro that for you, and then going to your talk. Professor Kendall Lee is a MD PhD. He joined the staff of Mayo Clinic in 2006 and holds the academic rank of Professor of Neurosurgery and also Biomedical Engineering at the Mayo Clinic College of Medicine and Science. In his clinical practice, Dr. Lee is an expert on neurological disorders, seeing patients with Parkinson's disease, Tourette syndrome, dystonia, and other neurodegenerative diseases. His research focused on developing deep brain stimulation for the treatment of Parkinson's, tremor, depression, OCD, and epilepsy. Dr. Lee is fascinated with the possibility of combining sophisticated electrophysiological recording with miniaturized analytical elements to augment or repair disrupted functions of the brain. Dr. Lee's research is funded by NIH, NINDS, and various foundations. His findings have been published in numerous high-impact peer-reviewed journals. He's an internationally recognized speaker and serves on the editorial boards for the Journal of Neuroengineering, Biomedical Engineering Letters, and Neuromodulations, etc. Dr. Lee has also received many awards and honors, include the Philip Gildenberg Award by the American Association of Neurological Surgeons and the Research Early Career Development Award for Clinician Scientists and Distinguished Team Science Award by the Mayo Clinic. With this, let's welcome Dr. Kendall Lee for his presentation.
Thank you so much. It's wonderful to be here with you. I wanted to, these are my disclosures, as you can see there. So deep brain stimulation, I think now everybody knows, is very well used. It's approved for essential tremor, Parkinson's, psychiatric disorders like obsessive compulsive disorder, but it's now being studied for depression, Tourette's, pain, Alzheimer's disease, and even addiction, drug addiction. So currently, DBS is used really in an open loop manner. But what's now being developed are what's called closed loop deep brain stimulation, where there are signals, biomarkers, like local field potential single units. And what I wanted to show you today, neurochemical recordings such as FSEV and MCSWV, which I'm going to explain to you about. So we know that the when we study the fMRI studies from patients, in this case from obsessive compulsive disorder, we can see the various brain networks that gets activated. And we have published these results from sort of the what's called bad contact versus the good contact. And we're seeing different neural circuits where the DBS is activating. And so the technology that we're studying at the Mayo Clinic is called fast-scan cyclic voltammetry, where on a carbon fiber electrode that you see there, a very rapid voltammetric scan is obtained. And when you give a dopamine analyte, you can see these kind of color, what's called color plots, where right here, the green is showing the dopamine signal. So as an example here, you can see on the x-axis here is the voltage while the current gets measured, and chemicals such as dopamine, which are oxidizable, oxidize at 0.6 volt while it reduces at just below 0 volt. While another type of neurotransmitter, adenosine, gets oxidized at about 1.5 volt. And then if you have combination of these, then you can see both the dopamine and adenosine oxidation. Now, before we were introducing this type of technology to human operating room, this is a picture from University of North Carolina, a device called Universal Electrochemistry Instrument. But such an instrument cannot be used in humans. And so at the Mayo Clinic, in collaboration with our Division of Engineering, we built our own device called WINCS system, which stands for Wireless Instantaneous Neurotransmitter Concentration Sensor System. And you can see a very simplified circuit there. So what I want to show you is the human recording.
So we have the WINCS system with the WINCS electrode in the patient. The patient is currently awake. And over here, you can see our WINCS wear analyzing the data that we're getting wirelessly in real time. Okay, we're going to make 1 millimeter advancement. Go ahead and advance, please.
There.
You're seeing the neurochemical changes there.
Place the background right before the insertion. Excellent. And
so what you just saw is one of the first neurochemical recording in a human patient undergoing deep brain stimulation. In addition to that, we developed another system called MINC system, which is Mayo Investigational Neuromodulation Control System that you see there. And here is a video of a pig that's implanted with such a system. And what you're seeing is we can wirelessly control the pig's behavior. This is an electrode that's been implanted into this pig's right nucleus accumbens, and you're seeing, because of the dopamine release, it's able to turn around. In addition, wirelessly, the pig is sleeping, you can turn on the stimulation and wake up the pig.
Fast phasing from 30 hertz to 50 microsecond.
Indicating we can now actually wirelessly control the pig's behavior. So when you look at the fMRI of the pig, just like this, you can see the various neural circuits, just like I showed you in humans, the activation from DBS. And what we have discovered using the WINC system is that nucleus accumbens DBS can now control the evoked dopamine release, as you can see there. That's the signal. In addition, I'm excited to introduce to you the second generation device that we made for the WINCS Harmony system, which now has 4 channels of the stimulation and 4 channels of the recording. And what you're seeing on the right is the 4 simultaneous electrochemical recordings of dopamine. In addition to that, our team also developed the software system for this called the WinxWare. This is the very first version of this. We have now subsequent versions, but you can see the splash screen that shows we decided to put the butterfly and the dopamine oxidation reduction potential on it to show you in US, there's this thing called butterfly effect. That small changes, flapping, for example, a butterfly in, for example, Australia can cause a hurricane in Florida just by critical dependence on initial conditions. Now, what I'm showing you here is the electrode development. So during DBS surgery, we use in neurosurgery a sensor, microelectrode, that can record electrophysiology. Here, what we have done is we have converted such an electrophysiologic electrode, but by adding a carbon fiber sensing tip that you see in D, the scanning electron micrograph, a carbon fiber sensing tip now can allow you to sense neurotransmitters such as dopamine and adenosine. But the one problem that we noticed with such sensors is that if you keep on using it, the electrode degrades. And you're seeing on day 1 the dopamine recordings here on top. But by day 3, a lot of the electrochemical recording of dopamine goes away because the carbon fiber has eroded. And that's why at Mayo Clinic, we have made a diamond reactor. And the reason is because diamond, remember, just like a carbon fiber, uses carbon, but with the diamond, it uses sp3 orbitals, which allows incredible stability. And here you see the first diamond that was created from our initial diamond reactor and the electrode. And then we tested this and identified that the stability was there, so that the dopamine recording, you can see day 1 and day 3 was nearly identical. And we published these results that we have deployed the diamond electrode, as you can see here, both in vitro in the flow cell, in vivo in the swine, as well as in vivo in humans undergoing deep brain stimulation. We have received Mayo IRB approval to do human WINX recording studies, as I showed you earlier in that video. Here. Not going to repeat this video, but as you can see here, a patient undergoing DBS has a WINX system that is being recorded. And what is exciting for us is that during these human WINX recordings, what we have identified is that during DBS, there's a effect called microthalamotomy effect, as you can see there in C, that the tremor goes away. And we have identified that the alleviation of the tremor occurs in conjunction with release of, in this case, adenosine. And the adenosine, we now know, appears to be coming from glia in the brain, from the release of glial transmitters such as ATP that gets converted to adenosine by an enzyme. And then this is our latest development system called WINX Maven, which is a multifunctional apparatus for voltammetry, electrophysiology, and neuromodulation. This is new technology that we have put into this system called MCSWV, a multi-cyclic score wave voltammetry. The system can also do FSEV, as I showed you earlier, as well as provide multi-channel electrophysiologic recordings and fixed potential amperometry with data acquisition and synchronized with neurostimulation. This is a slide showing you that before our group, there was no way to measure the absolute value, or what's called tonic dopamine measurements. On top, you can see the phasic measurements, but on the bottom, we can now measure the tonic measurements using multicyclic square wave voltammetry. I want to introduce to you, this is a photograph of Dr. Yunbei Oh, who received his PhD work at Hanyang University on this work, subsequently came to Mayo, did a postdoc, and now is associate professor of neurosurgery and biomedical engineering at Mayo Clinic having developed this technology called multi-cyclic square wave voltammetry, which combines the staircase voltammetric with the a square wave with the forward sweep and reverse sweep, creating the cyclic square wave or multi-cyclic square wave voltammetry. Such recordings allow us to do high dimensional voltammograms that allows us much better recording of the tonic levels. The biomedical engineering behind this is a little bit complex, so I'm not going to repeat that. I refer you to the publications from our group that published this. But in a nutshell, what this is able to do is show you using the absorption characteristics, in this case of dopamine, we can now measure the absolute value. Here, we're showing you the dopamine response to MCSWV, as you can see with the staircase potentials. In addition, another professor in the laboratory, Dr. Hojin Shin, has used similar technology now to measure serotonin recording using what's called the N-shaped MCSWV. As you can see there in A, you can see the difference with the forward sweep and the reverse sweep. There's a gap there. And now with the serotonin recording, you can see the signal in C, the oxidation reduction potentials. But we're now able to view this in a movie. What's exciting about this is that we have demonstrated and published that this is unique to serotonin using N-MCSWV, while things, neurotransmitters such as histamine or HIA or norepinephrine or dopamine, dopec, ascorbic acid, adenosine, or even pH changes do not show up, showing you the exquisite ability of this to really measure serotonin. Why is that important? Well, in this case, in a rat study, we can show you that escitalopram, which is a antidepressant very commonly used in human patients, you can see the gradual rise in serotonin in the brain. We're using this technology now to really study neurobiology of addiction, as well as I said earlier, both in China and now in US, neurosurgeons are using this technology for potential for treatment of drug addiction, which is really quite exciting. You can see the circuitry of this, where the dopamine now is coming from VTA, ventrotegmental area, being released in the nucleus accumbens. And this is work of one of my postdoctoral fellows in the lab, Jason Yoon. But I want to show you a video. As you can see here, this is now MCSWV being recorded in a rat nucleus accumbens. You can see we're now measuring moment-to-moment basal dopamine level here. We've just injected saline. As you can see, there's no change. But now, in a moment, we're going to inject cocaine. And look at that right there. That red, rapid rise of dopamine evoked by cocaine. And gradually, you can see it's coming down. But the basal level with time goes even below the control levels, indicating why these cocaine addicts might need, again, another dose of cocaine. What's exciting for us is that here, what you're seeing is now we can modulate this with DBS. So I'm going to now play this video, again, recording tonic dopamine. But first, we're going to deliver DBS, deep brain stimulation, into the brain. And what you can see here, here's the control. We're going to turn on the DBS system. And notice what happens to the basal dopamine level. Goes down, gradually comes back to baseline. And now the same amount of, here's the saline being injected just for control. But now we're going to inject cocaine. But notice that there is no rapid rise of dopamine system. These are really exciting results that suggest the mechanism by which DBS may be able to treat drug addiction. So with that, what all of these type of systems are indicating is that with smart DBS systems, now these are closed loop deep brain stimulation that can use biochemical as well as electrophysiologic feedback, as you can see there. Neurotransmitters such as acetylcholine, glutamate, adenosine, serotonin, dopamine may be measured, as well as local field potential single units using technologies such as FSCV, MCSWV, and barometry, and advanced analysis techniques to now have a closed loop system that you see on the right where DBS and neurochemical and electrophysiologic recordings can be done, and we can have a personalized modulation parameters. So with that, I really want to thank the organizers for allowing me to speak today. The funding for this has been from Mayo Foundation, Granger Foundation, as well as Brain Initiative, the National Institute of Health. I want to show you a recent photo of our team at the Mayo Clinic. Behind them, you see this is called the Foundation House, where the brothers Mayo used to live. This is, I also want to acknowledge the work of Dr. Kevin Bennett, Charles Blaha, Yun Beio, Hu Jinshin, Aaron Rushin, Jason Yoon, and Abi Goyle. Thank you so much for allowing me to speak. I'll be happy to answer any questions.
All right, thank you, Professor Lee. And this is a very interesting talk, and we see another dimension, chemical dimension, besides the electrical interface. So let's start from the question from the audience. So, Professor Lee, if the chemical electrode is obstructed by intracranially inflammatory precipitation, then what is the solution for this condition? I guess.
Yes, that's a
chemical thing. Yeah.
Yes, that's an excellent question, and one of the key issues in neural interfaces. So these type of recording systems, we know one of the key problems is glial scar. You know, when you say obstructed, we now know what the mechanism of that obstruction is. It's really glial scar that can impede recording. But I can tell you, these electrodes are incredibly small. You know, they are like, 10 microns in diameter. Some are, and so other researchers have demonstrated that such recording using these carbon fibers can last for months. And so I think that in the future, what will happen is we will develop, as already being developed, these chronic sensors. Now, one aspect, of course, as I presented to you, we went with diamond recordings because of the erosion of the carbon fiber. But I think that, these challenges, I think your question is a very good question because it raises what the potential future challenges of this technology are.
Yep. I see. So, so that basically means that it is an issue, but you're actually solving that problem, and it will be very likely that there will be long-term, chronic, durable probes for those things.
That's right. I didn't present here, but in 2 years ago, a closed-loop system has been introduced called the Percept system by Medtronic. And in that system, they're able to record chronic electrophysiologic recordings. At Mayo, we published our early results using this. There is no current chronic human electrochemical system yet, but that's the technology that we are building at the Mayo Clinic.
I see. Yeah. And that's, I think that's, yeah. Sorry, that's exactly linking to the next question from the audience. The one audience is asking, when will the serotonin and dopamine probes going to be able to use in actual human, and what the temporal resolution might achieve? Would that achieve really real-time temporal resolution? Yeah. So
yes. What's really exciting about this is, and then I have to disclose here also, at the Mayo Clinic, there's a new program that Mayo physicians are now allowed to do what's called employee entrepreneurial program. And just recently, we've been able to start a company because we want to provide this technology to everybody. And so this technology is being developed in a company so that it can be deployed. It hasn't been done yet, but at least a company has started. So that's one called Navinetics Neuromodulation. And then in terms of temporal resolution, this is called fast scan cyclic voltammetry because it's doing 400 volts per second. But the voltage excursion you need is only about 1.5 volts, as I showed you, which means that you can do a set using fast scan cyclic voltammetry, a recording in 10 milliseconds. So one recording of dopamine can occur in 10 milliseconds.
I see. Yeah. Another question is, I think, is on the spatial resolution thing. So, Dr. Lee, you know that the DBS system has directional leads which entered more channels. Would it be beneficial to have multiple channel dopamine probes or chemical probes would that be helpful for human clinical treatment?
I absolutely think so. That's another excellent point, because what I think ultimately we need is to probe the brain in multiple areas. As I showed you with the fMRI studies, that DBS is really affecting the brain in circuit. And so what we envision is perhaps a DBS stimulating electrode. For example, let's talk about drug addiction. You know, one area that's been tested is nucleus accumbens. But what we see is that perhaps a better area might be VTA, ventrotegmental area, that actually sends the dopamine fibers to the nucleus accumbens. But then the sensing component may be separate from where the stimulation electrodes are because of the circuitry of the brain. And so in that case, you know, I just showed you some of our exciting results coming out in the lab right now, where perhaps when we stimulate the VTA, ventrotegmental area, and record in the nucleus accumbens, we're controlling the release of dopamine by the VTA in the nucleus accumbens. And the exciting data that I'm just showing is that by modulating these brain circuits, you can now modulate the effect of drugs of abuse like cocaine. We have now tested other drugs as well, such as opioids. And the effect appears to be very similar.
I see. Yeah, and condition on the time, we'll have the last question. So that's a quite general one, Professor Lee. So how do you comment on the pros and cons of electrical probes and chemical probes? What are the advantages and disadvantages? And what chemical probes together with electrical probes can ultimately give us for the treatment of neurological diseases?
Yes, I think, you know, that's a very complicated question. But a simple way to answer, I think, is we are now in very early stages of probing the brain's neurochemistry in vivo. You know, this is technology that's being developed now. And so likely what's going to happen in the future is additional research will be necessary to more precisely define how that electrochemical recordings, just like, you know, we have much more experience with electrophysiology, which is now almost 100 years. While electrochemistry, now it's only been, you know, maybe a couple of decades. And the introduction of such technology into humans is just now beginning. But what I will say is that oftentimes I think people, you know, there's a very interesting thing we say in US, which is everyone overestimates where we'll be in 5 years, but underestimates where we will be in 10 years, which is almost sounds like a paradox. But I think that if you look at even deep brain stimulation, as I said, now we have percept systems that actually we're on the verge of closing the loop on the brain stimulation technology. I will point you to the technology in the heart. Cardiologists now regularly use sensing technology for their cardiac pacemakers. And I think what's going to happen is in neurosurgery, the technology is going to rapidly advance so that we can sort of catch up to what the cardiologists have done with their pacemaker system, because really DBS is a brain pacemaker.
Yep. All right. Thank you, Professor Lee. And so based on the time, so we'll end Professor Lee's session right now. And this is the last talk for our forum. And we would like to thank all the speakers and invite Professor Lu-Ming Lee to provide us the ending remark for this forum on brain-machine interface and neuromodulation. Professor Lee.
Hi, Kendall. Hi, Lee, Professor Lee. Yeah. Nice
Thank you.
Yeah. Long time no see you. Thank you very much for the invited speakers. On the machine interface, brain-machine interface, and neuromodulation. I think it's a very exciting field. And the last, as Dr. Lee mentioned about this area. Also, I in the last 20 years do the research on the neuromodulation, particularly some of the deep brain stimulation. Now we also looking for the field direction, and this forum, the plenary speakers give wonderful talk on the brain-machine interface and the neuromodulation technology. I think this is will encourage us to connection each other to inspire the new idea for the new technology to help patients in the future. So I'm very thankful for enjoy the forum, and thank you very much for the speakers to give a wonderful talk, and thank you very much.
All
so
right.
This is the end of the forum, this session. Yeah, thank you very much. Yeah.